All right. Well, thank you, Joel and Rolf and the organizers of this conference for giving me the opportunity to present some of our activities that I've been involved in at UCLA. I wear a couple different hats, but I'm primarily Associate Director for our minor in biomedical research. So I'm a big believer in depth over breadth, and I'm going to completely ignore that. Unfortunately, I'm going to try to address three different areas that I've been involved in the next 12 minutes, so we'll see how that works. So I'm going to tell you about our minor in biomedical research. This is a high-impact program that is focused, is basically an entire curriculum built to support undergraduate students in intensive research experiences throughout their time in college. I'll then talk a little bit about our research deconstruction model, and finally our inclusive excellence program that's been funded by HHMI. So these are the people who have basically been responsible for the minor. This all grew out of, I'm trying to see what my laser pointer is here. Is this, nope. There we go, okay. Oh, perfect, thanks. So the minor was basically an institutional level scale up of Utpal Banerjee's HHMI Professors Program. So it pretty much grew out of the work that he was doing dating back to 2002. The minor actually was launched in 2007. Utpal stepped down about a year ago as our director, and we were very fortunate to have Tracy Johnson on campus, another HHMI professor. She brought in elements of her program, which have been integrated with the minor. She's also the PI of our Inclusive Excellence program. And down here is an amazing set of instructors who've really done most of the heavy lifting in terms of teaching the courses. So this flow chart kind of shows you the organization of our biomedical research program. We've got introductory courses that are open to students from any major. They're primarily geared to first, second year students, novice students who maybe have never been exposed to research at all, new transfer students as well, and then students who take one of these courses can apply to join our minor in biomedical research. So we offer these courses every quarter, fall, winter, and spring. We run application cycles every quarter. We take about 25 to 30 students each quarter, so about 75 to 90 students join this program each year. So as I said, this is a curriculum that's built around undergraduate research. So our students are required to do at least 4 quarters of letter-graded research, the 199 courses at UCLA, or other versions of letter-graded research, culminating ultimately in a thesis. We don't feel that it's fair to tell our students you have to do all of this research to complete the minor. Good luck finding a lab. We'll see you in a couple of years. So I meet with every student who joins the minor. Maybe about 1/3 of them already have a lab that they're working in, but about 2/3 don't. And I meet with each one of those and help to place them in one of the labs on campus where we know the mentorship is going to be strong. In addition, our students have to take 5 other courses. They have to take an advanced version of a research deconstruction course that I'll tell you about in a couple of minutes. They take a journal club class with us, a seminar class where they present a seminar on the research that they're doing in their lab. And this is an interdisciplinary curriculum, so we also have a GE course in biomedical ethics that they have to take, and they have to take an upper division elective in history or philosophy or sociology of science. So I just want to show you 3 outcomes from this program that we've been running for the past 11 years. The first is that we've got well over 600 students who have done research in over 200 labs at UCLA, at the college, the School of Medicine, the School of Engineering, because we've got several bioengineering students, 38 different departments. So we're really engaging, not only are these students getting great research experiences, but we're engaging a large fraction of the research community in teaching our students. Second is that the students, not surprisingly, after working in the lab for a year, year and a half, in many cases 2 years, actually get some serious science done in their work. So 213 of our students are co-authors on a peer-reviewed publication from their undergraduate lab, 290 publications total, 20 of which our first author papers by one of our undergrads. And 42% of our alumni from the program have at least one paper from their undergraduate research. And then we've looked to see where our students go after they graduate. So if we allow for 2 gap years, we find that 80% of our alumni have matriculated to a higher degree program. If we take that 80% and then break it down to see where the students are going, nearly half of them are going to PhD or MD PhD programs, and a little over 40% to MD programs. We've also had students go to pharmacy, dental, a couple to law school. But the students leave this program really well prepared to enter the next phase of their education. So this is a high impact program, but it's the culmination of, I think, also introductory courses that we have. So I want to take the next few minutes to tell you about our research deconstruction model. And this is something that started when we developed the minor. So initially, in Utpal's original program, he had this cure that could service about 20 to 25 students per quarter, and then students would go into an advanced version where they would do higher level research. When we wanted to scale up, we needed a model that would allow us to scale up. We couldn't obtain 5 more classes, laboratory classroom spaces to scale up our cure. So Utpal had this idea of that ultimately developed into our research deconstruction course. So this is our primary feeder course for students to enter the minor. So how does it work? This is again primarily for first and second year students, new transfer students, novice students who've never seen research before. What we do is we bring in one of the UCLA faculty to deliver their regular roadshow PhD level seminar. So it's got buzzwords, jargon that the students have never seen, concepts they've never seen. It's the same seminar that they would give as an invited speaker at another campus or at a national conference. So the students are lost. They don't understand a word. We tell them that's okay. We videotape the seminar, we put it on a course website, and the students can watch it as many times as they need to. And then the instructor of the course, who is not the invited speaker, it's a dedicated instructor for the course, breaks down that seminar over the next several classes with the students, teaching them some of the background science, identifying some of the major questions, some of the more specific aims for that particular project, looking at some of the experiments that were designed, and so on. Our problem sets are all take-home assignments that emphasize higher order skills like designing experiments, identifying controls, and so on. At the end of this series of 7 classes, we bring the speaker back for a Q&A session. By this time, these students who were lost at the beginning actually know this work really well. And they ask questions that are surprisingly sophisticated. It's not uncommon, in fact, it's actually very common, for our speakers to say, you know what, I get asked that question all the time when I give this talk. Or the reviewers of our last grant asked us this, and to be honest, we don't really know the answer, but this is what we're thinking about. And so I think the students really, again, feel empowered. That's the feedback that we're getting. So I'll try to go through this very quickly because I don't want to take too much time on it. This is an example of how this might work. So this is a seminar that I deconstructed a while back by Tim Lane on Wnt signaling in breast cancer. It basically followed a genes in development paper that he had just published, but we used the seminar primarily as the delivery vehicle. So in teaching this work, I was able to teach the students a little bit about cancer biology, cell signaling, cell cycle, ubiquitin-mediated proteolysis, but they're learning all of it in the context of the actual research project. We discussed a number of different experiments, which meant we got into techniques like transgenics, RT-PCR, RNAi, co-IPs, and we got to talk about what sorts of controls get built into experiments like that. And the students also get to look at the data and learn how to interpret it. All right, so there's actually a lot that you can teach from just one seminar. So this is a little bit of data. We've been running the CURE survey for the past 10 years. This is self-reported data, so this is what the students feel they're getting out of the course. And you can see, and our students are the red triangles up here. The students are reporting that they feel that they've learned more about how scientists think, how to interpret results, how knowledge is constructed. These are kind of core elements of the process of science and scientific inquiry. And again, they're reporting higher levels than students who participate in a summer research internship. We've also looked at what happens to our students years after they take this course. So we've been running the courses for over 10 years, and what we've found is that if we look at students who were enrolled STEM majors when they took the class, nearly 90% of them are completing a degree in STEM within 5 to 6 years of being in college. And this is comparable to what we see with our cure, and it's significantly higher than the UCLA averages overall, which themselves are higher than the national averages. For underrepresented students, we also see high levels of STEM retention, not quite as high as our cure, although the sample sizes are much smaller here, but again, more than the UCLA averages. So we think that research deconstruction can provide an alternative to cures that may be more scalable. It's a way of introducing students to the process by which scientific inquiry is done, so kind of like a research experience, but they really actually go in deep and see the logic of the research, which you don't always get from a lab experience, unless you've been in there for a while. It's low cost. There's no lab space required. There's no lab infrastructure. So it's inexpensive to implement and sustain. As you've seen, the students at least feel that they're gaining knowledge about how scientific research is done, and it may result in high STEM persistence. So we think that this might have a value proposition for many campuses, and in particular community colleges where resources are often limited. So with help from the NSF, over the last year, we've piloted a research deconstruction course at Santa Monica College. Rashida Hawk has been our instructor for that. We've run 2 offerings. We're in the middle of the second offering, and we're hoping to develop future partnerships with other community colleges. So I'll just take a couple of minutes to tell you at the very end about our Inclusive Excellence Program. So this is an HHMI funded program to provide, to basically bring more students to the table for achieving excellence in STEM from all different backgrounds and areas. Our focus has been on the transfer student population. So this team is led by Tracy Johnson, who's the PI of the grant. Aaron Sanders and Mark Levis Fitzgerald and Rachel Tennyson have also been really valuable members of the team, and they've all brought their individual talents to the table on this. So this is the problem that we're focusing on. Transfer students, at least at UCLA, face a number of barriers to entering STEM majors and achieving excellence in STEM. 40% of the undergraduates at UCLA are transfer students. 40% of UCLA undergrads are transfer students, but only 16% of the life science majors are. So transfer students are hitting barriers just entering STEM majors. Once they get to UCLA, only 20% actually do research in labs as compared to 40% of freshman entry students. And this is a very diverse population. 34% are underrepresented, 40% are first generation, 50% are Pell Grant recipients. So the barriers, we believe, are structural and also pedagogical. What are the experiences that the students are getting in the classroom? So our approach has been to modify, make changes to the curriculum. This has been we've made a lot of progress in the life sciences core curriculum. Deb Piers is here from the core curriculum, and that program has been condensed from a 4-course series to a 3-course series to try to give students an easier path to the upper div courses and also align better with what students are taking at the community colleges. We've run workshops to train faculty in best practices for more inclusive classrooms, and we're also trying to expand access to high-impact programs like the minor, so more transfer students can get involved in that. The hope is that this will ultimately lead to higher numbers of transfer students who graduate with degrees in STEM, who get research experience and are well prepared to pursue higher degrees. Overarching all of this is data collection, and Mark Levis Fitzgerald has really been taking the lead on this. So we're trying to collect data to better understand what the barriers are, as well as understand the impact of these changes. So with that, I just want to thank the people who've been responsible for this. Utpal basically started it all, and Tracy Johnson, who's been leading us for the last year and a half or so. Fantastic instructional team, colleagues with the Inclusive Excellence Program. Mark Levis Fitzgerald and Casey Shapiro have been leading our assessment for the minor and for all these other components I talked about. People from SMC, current and former deans at UCLA, and of course HHMI and NSF, without whose support this wouldn't be possible. Thank you.